This video provides instructions for neural network training for question 4 in homework 2. Let's start. First, we have the file we provided you on coursework right here, nnns.tar.gz. Let's unpack the files. All right. Let's go to NNs. You will see a couple of files here, a couple of directories. First, let's look how we go about running a model. For that, you go to job outputs, and what you do is you call Caffe. Specify train. Specify the solver we'll use. The solver is specified in the homework. Is called one layer prototext here, and all the solvers will be in this directory called solvers. All right, then you run this, and Caffe will do its thing. All right, let's kill this thing. You will see that it prints out a lot of things, but before we look at those in detail, let's look at the actual solver file. So that's in solvers, colon one layer. Okay, so this file has two parts. The first part specifies the actual training procedure, validation, and model snapshotting. Let's look at these one by one. We've got our initial learning rate, the momentum, how often we run a validation test, how often we display the training performance, the maximum number of training iterations, how often we actually save the model, which means we save the architecture and the actual parameters. This is where the model will be saved and its parameters. This specifies the auto-regularization, the learning rate decay schedule. These things are not as important for your homework purposes. The random seed, using a CPU to compute everything. Test state doesn't matter. However, test iteration, let's look at this. So what this means is when it runs the validation test, it will first load the validation data based on this layer here. And as you can see, we have two of these layers, one for training, one for testing, specified by the phase. If you look at the actual layer, basically what it does, it reads in this file here, either the train.0.caffe or the valid.0.caffe. And then from that, it reads in what we call data and what we call the label. And then to run iterations, whether it's for training purposes or for testing purposes. And in each iteration, it will use this many examples specified by the batch size. Now what happens is in the validation data here, you have 863 files exactly, and we lump them all into one batch size. So that's why we have one iteration here, because you need a single batch to get a full validation test. However, in the training, there's something like 3,100 files or so. And the batch size here, it comes out to be about 1/5, I think. The shuffle means that we actually randomly select 680 examples. The scaling has to do with the fact that our data is stored in PNGs, and we have to scale the PNG values, which are actually integers going up to 255 down to the 0 to 1 range. All right, so before we look at the actual data here, what we know is the data consists of 93 features in each example. Let's look at the actual network architecture and what we have in this model. So first we have a fully connected layer, specified here by its name, type, its input, the output. What's important here is the number of hidden units. This is the number you will have to modify for your homework. Here we have the actual initialization of the parameters. It doesn't matter for your homework purposes. The next thing is the actual activation function through which you pass the outputs of this fully connected layer. We use rectified linear units, specified here. in the layer type. Then I have an optional layer which applies dropout regularization. You can uncomment it if you want to use it. Then you have your final fully connected layer, which has 3 outputs, 1 for each class. These outputs then go through a softmax layer, which computes the loss between the probabilities that you have for each class and the actual label, and it will output the loss, and you have a similar layer to that which will output the accuracy. Okay, so now let's look quickly at the data files. So you have 3 of them. You have the train valid Caffe right here. This has all of the files, training and validation. And each row in here basically specifies for that specific example the label on the right, and on the left the PNG containing the feature values. And we have provided you with the default train and validation split right here. Basically puts 80% of the data in training, 20% in validation. These actual PNGs, if you actually want to look at them, you'll find them inside job outputs right here. This is the directory containing them. And now what we'll do is rerun Caffe. This time I'll actually save the Caffe printout right here. Okay, so then you can look at your printout. Let's kill this process for a moment. Let's look at the latest printout, and here we go. Caffe has finished about 700 iterations, and what you will see is exactly what you specified in the model specification file. You have testing here, the testing performance, the accuracy, and the loss. This gets printed every 10 iterations, so here we are at 680, at iteration 690, and iteration 700. Similarly, you have the training performance, which gets printed every 5 iterations. Other things you'll see in here are the actual learning rate at those iterations. As you can see, it gets decayed over time based on the schedule was specified. And basically what you will need to do here is start from this one layer prototext model, and your goal is to modify it such that the test performance, the actual performance on the test set, will outperform everything, all the test accuracies that you saw in the figure from the paper. Now here's the thing, if you go back here and look at your files, you don't actually have the test data. We'll use the test data on our end to evaluate your models. So what you will need to send us are 2 things. First, you need to send us the actual model file which we'll use for testing. These files are located in testing. You will see one file for each model in solvers. You will see a corresponding file here in testing. If we look at this file here quickly, it's the same as the other file. It just skips all the parts that specify training validation. We don't do that anymore. We just do a single test. It specifies the batch size for the test and the model architecture. So this is the actual structure of the model. The other thing you send us are the parameters. The parameters you'll find in snapshots. And go to one layer. There's one directory for each model. Here you see all the snapshots. Now, before you send us any files, you should run a sanity check yourself, test the model to see that it does what it should. So here's an example test. Let's look for a second here. At iteration 700, our test performance here is 88.876. Okay, so we're going to run a test, an actual test of the model on the validation data, and see that you get the same performance. And the way you do this is you call Caffe again. This time you specify test, you specify model. The model is the one that you have in testing. And the next thing you specify are the weights. The weights are given by the snapshot. In this case, we use this snapshot right here. And the last thing is the iterations, which by default is going to be 1. And the reason it's 1 is our batch size includes inside it all the validation examples. Alright, let's see what happens. As you can see, we get this accuracy here, 88.876, the same accuracy that we had in the process of training and validating the model. So this is the sanity check you should run before you send us the final files. So the files you send us, just to clarify, are the model specification inside the testing directory and the .caffe model, which in this case is snapshot 700. It would be this file right here. And then on our end, we'll run these model weights and your model specification on the test data and see if you truly outperform the methods in the paper. So that's basic usage of Caffe and an outline of part B of question 4. Good luck.